Good morning, everyone. A very good morning. Shall we begin the session? One more thing that I want to, yes, please submit the assignments on the time because this is the high time and we want to finish this course by end of this month and around 15 days, 20 days are left in this month. So please submit the assignments well in time so that we can issue the certificates to you. Otherwise, there's a problem if you don't submit the assignment. There are few assignments that are pending, few assignments that you have done. So there is no usage of the submitted assignment. So please submit the assignment. It's a reminder. Yeah, each and every assignment have a unique code, unique grade. So shall we begin the today's session? Today's topic is functional dependencies. In the last class, we have started with the relational database design. I'm continuing with this, that is the functional dependencies, how the functional dependencies or how one part is depending on the another part, how one methodology will be decomposed into the relation schema, how this evaluation will be done in the functional dependencies, how we are talking about each other, that is recalling the introduction in the relation algebra, that is used for the set of the attributes and that is used for the uppercase. Okay, all right. Now let's move to the next method, that is the formal methodology, in which there is a dependency that is talking about within the chapter number 2 also, that is based on the concept of the keys and the functional dependencies, in which the keys are also used for the dependency schedule. In general, we use a Greek letter for the set of the attribute, for example alpha, and we use a lower case Roman letter followed by an uppercase Roman letter in the parenthesis to refer to the relation schema. So we use the notation RR to show that the schema is for the relation R, with the R denoting the set of the attributes. But at the same time, simplify our notation to use just R when the relation name does not matter to us. So of course, our relation schema is a set of the attributes, but not all set of attributes are schema. So when we use a lowercase Greek letter, we are referring to a set of the attribute that may or may not be a schema. So a Roman letter is used when we wish to indicate that the set of the attributes is definitely a schema. And when a set of the attribute is a superkey, so we denote it by K. And a superkey pertains to a specific relation schema, so we use the terminology K is a superkey of the R. So we use a lowercase for the relations, and in our example, these names are intended to be realistic. For example, instructor, while in our definitions and the algorithms, we use a single letters like R. And a relation, of course, have a particular value at any given time. So we refer to that instance and use the term instance of R. And when it is clear that we are talking about an instance, so we may use simply the relation name, that is, for example, the R. Now, what are the various keys and the functional dependencies? So database models a set of the attributes or entity and relationship in the real world, and there are usually a variety of the constraints on the data in the real world. For example, some of the constraints that we are expected to hold in university examples of database are student and the instructors are uniquely identified by their unique ID. And each student and instructor have at least only one name, at least, or we can say the one name that is published, that is available within the range that is used within the department name. And each instructor and the student is associated with only one department. There is only one department that is associated with the instructor and the student. And each and every department has only one value for its budget and only one associated building. An instance of that relation that satisfy all such real world constraints is known as the legal instance of the relation. That legal instance is one where all the relation instances are the legal instances. And some of the most commonly used types of real-world constraints can be represented formally as a keys, that is used with the superkey, candidate key, primary key, or as a functional dependencies. So we define the notion of a superkey as a set of one or more attribute that is taken together with a set of the defined values. What are the defined values? What are the functional dependencies? That is given below. So we define the notation of a superkey as a set of one or more attribute that we taken collectively to identify uniquely a tuple in the relation. So we restate the definition as we use as a uniquely tuple in that relation. So let R be a relation schema. So a subset K of R is a super key of the R if in any legal instance of R for all pairs T1 and the T2 for the tuples is an instant of the R. If that is not equal, so again pairing for that K is also not equal. That is, no two tuples in any legal relation may have the same value on the attribute set K. Now, next example is if no tuples in the R have a same value on the K, then a K value uniquely identifies a tuple in R. Whereas a super key is a set of the attribute that uniquely identifies an entire tuple, then functional dependency also allows to express constraint that uniquely identify the values of the certain attributes, whatever the value that is given with the certain attributes. So consider a relation schema R and let alpha is belongs to the R and beta is also belongs to the R that satisfy the functional dependencies for which the tuples T1 and the T2 are the instances such that T1 T2 is the case and T1 T2 or T1b is equals to the T2b. That is the tuple 1 of beta is equals to the tuple 2 of the beta. And we say that the functional dependency A alpha belongs to B holds on schema R if in every legal instance R satisfies the functional dependency. It means that it is a super key of the R if the functional dependency holds on R. In other words, it's a super key for every legal instance of the R. And for every tuple T1 and the T2 from the instance whenever T1k is equals to the T2k. And it's also the case that T1r equals to T2r, that is T1 equals to T2. And functional dependencies also allows to express constraint that we cannot express with the super key. So we consider the schema instructor department ID name, salary department name, building budget, in which the functional dependency department name budget holds because for each department that is identified by a department name, there is a unique budget amount. So we denote the fact that the pair of the attributes ID and the department name forms a super key for the instructor department by writing ID department name, salary, building budget. So we shall use functional dependencies in two ways: to test the instances of the relation to see whether they satisfy a given set F of the functional dependencies or not, to specify the constraints on the set of the legal relations. So we shall therefore concern ourselves with only those relation instances that satisfy a given set of the functional dependencies. And if we wish to constrain ourselves to relation on the schema R that satisfy a set F of the functional dependency in which it holds on the R. There are four parts A, B, C, D that tuples have a same relation, C values C1, and no two tuples have a same value C2. And there are no other pairs of the distinct tuple that have a same A value. And this functional dependency is not satisfied, however, to consider the tuple A T1, A2, B3, C2, D3. And T2, A3, B3, C2, D4. These two tuples have the same C values, C2, but they have a different A values, A2 and A3. Therefore, we found a pair of the tuple T1 and the T2 such that T1C is equal to T2C. And these some functional dependencies are said to be trivial because they are satisfied by all the relations, and this is satisfied by all the relations in the instances that reading the definition of the functional dependency literally for all the tuples T1 and the T2, so that T1 is belongs to A is equals to T2 belongs to A. It is the case that T1A is equals to T2A. Similarly, AB also belongs to A, that is also satisfied with the relations involving the attributes A. Now next is boy code normal form. This is also desirable with the BCN. This is a BCNF, that is a boy code normal form. This eliminates all the redundancy that can be discovered based on the functional dependencies, and there may be some other types of redundancy that are also remaining, and the relation schema R in BCNF with respect to the set F that is denoted with the BCNF of the fact that it is available or it is used in the BCNF concept that is other types of the dependencies also that is available with the database remaining, and the relation schema R is in BCNF with respect to a set F of the functional dependencies, if for all functional dependencies in F1 plus of the form alpha belongs to beta, where A belongs to or A contained in the R and beta also contained in the R, at least one of the following holds: that alpha is belong to the beta is a trivial functional dependency, that is the beta is belongs to the alpha. The alpha is a super key of the function for the schema R. And this is the and database design is in the BCNF if each member of the set relation that constitutes a design is in BCNF. And this is another example of the relation schema that is not in BCNF. That is the instructor department, ID name, salary, department name, building budget, and the functional dependency department name, budget holds on instructor department, which also satisfied with the department name that does not have a special keys with a department that may have a number of the different instructors. And we saw that the decomposition method, whatever the decomposition method, and the instructed schema is in BCNF, all of the non-trivial dependency or functional dependency that holds, such as ID name, department name, includes ID on the left side of the arrow. And similarly, the department schema is in BCNF because all of its non-trivial functional dependency that also holds, such as the department name, building budget. That includes department name on the left side of the arrow. Department name is a super key for the department, and that department is also in a BCNF. Now we now state a general rule for decomposing that are in a BCNF. Let R be a schema that is not in BCNF. Then there is at least one non-trivial functional dependency. Alpha belongs to B, so that alpha is not a super key for the R. So we replace the R in our design with the two schemas, alpha union beta, and relation is belongs to or that is divided or that is excluded from the beta and the alpha. And in the case of the instructor department, that alpha equals to beta name, department name, and beta equals to building budget, that is replaced by the alpha union beta, department name, building budget, and relation beta minus a, that is ID name, department name, salary. And in this example, it turns out to be beta minus alpha, that is a beta only. And we need to state the rules as we did so to deal correctly with the functional dependencies that have some attributes, that have some values that appears on both sides of the arrow. The technical reason that are covered over here, that is in the BCNF, but at least one or more resulting schemas are not in the BCNF. And in such cases, further decomposition is also required eventually, which is a set of the BCNF schemas. And we've also seen several ways in which to express the database consistency constraints, primary key constraints, functional dependencies, check constraint, and assertions triggers. Now testing these constraints each time when the database is updated and costly. That means when it is a costly or when it is updated very much quickly. So this is the way how it is, how the functional dependencies are tested out. That will be done by using the functional dependencies in some cases. For example, to the design, a student may have only one advisor. This follows from the relationship set advisor being many to one from student to advisor. And the small change we shall make is that an instructor can be associated with only a single department and a student can have more than one advisor, but at most one from a given department. And one way to implement this change using the ER design is by replacing the advisors relationship set with a ternary relationship set, department advisor, involving entity set, instructor, department, the student. That is many to one from the pair to the department. This is a department that contains three fields, three attributes, department name, building budget, instructor, that again 3 attribute ID name and the salary, student 3 attribute ID name and the total credit. So this is the many-to-one relationship that shows, or this ER diagram shows, specify the constraint that a student can have more than one advisor, but at most one corresponding to a given department. With this new ER diagram, the schema for the instructor, department, and the student are unchanged. However, the schema derived from the department advisor is now department advisor, SID, IID, department name. And this cannot specified in the ER diagram. Suppose we have identical constraint that an instructor can act as an advisor for only a single department. This will be used for the department advisor, IID, department name, SID, department name, IID. This will be used for the requirement that an instructor can act as advisor for only one department. This is the SID, IID, IID, department name. And both the above schemas that are in the BCNF, that also verifies that any schema with only 2 attributes must also belong to BCNF by the definition that includes all the attributes appeared in the functional dependency. That may be SID, that may be a department name, that may be a DID or the IID. The next is the 3NF. That relaxes this constraint slightly by allowing the certain non-trivial functional dependencies whose left side is not a super key. And before we define 3NF, we recall that a candidate key is a minimum super key, that is a super key not proper subset of which is also a super key. So this also belongs to third normal form with respect to the set F of the functional dependencies. So alpha belongs to beta, is a trivial functional dependency. Alpha is a super key, and each attribute is contained in the candidate key for the R. And note that the third condition above does not say that a single attribute or single candidate key must contain all the attributes in the beta and the alpha. Each attribute A in the beta that may also contained in a different candidate key, and the first two alternatives are same as the first alternative that will be used with the 3NF with the definitions of the BCNF. And observe that any schema that satisfies BCNF also satisfies the 3NF, because every dependency that is included in the 3NF that is also satisfied with the BCNF. Next to the higher normal form, that is a higher normal form means more than one normal form that is carried out with schema that includes a phone number, that includes a, yeah, this is not mandatory to, or it is not sufficient to avoid the unnecessary repetition, but also use the entity set definition in which we record with each instructor set of the student or children's name, set of the phone number. That means that can be shared by the multiple people. Therefore, phone number, child name must be multi-valued attributes, and these rules are guaranteed schema that also forms an ER design. So we have two schemas, one for the multi-valued attributes, phone number, and the child name. One is ID, then child name, ID, then phone number. And if we were to combine these schemas to get ID, child name, and the phone number, 3 parts, because ID and the ID is same in both the cases. So we would find the result to be in the BCNF because only non-trivial function dependencies holds, and there are two children named David and the William that have a same phone number. This is a 1234. This is a 4321. This is only the same. This is only the different, not the same. First and last tuple we have recorded the dependent names and functional dependency that is included in this one. Next, this is the theory of the functional dependencies. This is the closer relationship that we have done. Closer, this we have done. Canonical form we have done. Lossless decomposition, that is the next part that I'm going to take in the next class, that is in the tomorrow's class. So till now, any doubts, anyone? Okay, all right. So again, my suggestion is to submit the assignments on the time so that we can finish the course on the time. All right.